You already know that salts tend to be solid at room temperature, where molecular compounds can be solid, but they could also be liquid and gas. You already know that salts, when dissolved in water, will conduct electricity, but even a soluble molecular compound never will conduct electricity. The properties of compounds that you see, like solubility, conductivity, phase at room temperature, all depend on the type of bonding that forms the compound. We can use electronegativity values for the material, for the elements that are bonding with each other, to determine what type of bond we have by finding the difference in those electronegativity values. Difference, I just mean subtraction. Take the two electronegativity values and subtract them. But what is electronegativity? Why will subtracting them give me information about the type of bond? Electronegativity is a property of elements that indicates how likely an atom is to pull electrons in towards the nucleus of that atom. We're talking about pull electrons that are being shared in a chemical bond specifically. Unlike electron affinity or ionization energy, those were energies. Electronegativity is not an energy. It's not measured in joules. It doesn't even have a unit. This is more like a scale or a ranking about how likely an atom is to pull electrons in towards the nucleus of that atom when those electrons are being shared between two atoms in a covalent bond. This periodic table represents the electronegativity values of the elements that are measured. A couple of things to notice. There's one red one. That's fluorine. Red is the largest value. Its value is 4.0. Blue indicates the smaller values. The smallest value, look to the left at the bottom, at francium. It's only 0.7. So the numbers on this scale run from 0 to 4. Look at group 18, noble gases. You see they don't even have any, with the exception of xenon. Xenon, with huge zaps of electricity, can be forced to form bonds with other atoms, only because it's very large with so many electrons, 54. But the rest of the noble gases do not tend to form bonds and thus don't have an electronegativity value. So when we consider the electronegativity numbers of two atoms, we want to see what type of bond forms between them. If the difference is very large, like the difference between metals on the left and nonmetals on the right, the large difference may indicate the bond between the two atoms may be ionic. As you already know, a salt is formed from a metal cation and a nonmetal anion. If the electronegativity difference is very small, as might be found between two adjacent atoms, the type of bond between those two atoms may be covalent. As an example, let's prove what type of bond forms between potassium and chlorine. Using the electronegativity table, a reference sheet you would always have with you when you're asked to use it to find situations like this, we find that the electronegativity value for potassium is 0.8. The electronegativity value for chlorine is 3.0. So the difference in electronegativity would be, and I always just do the larger minus the smaller, but if you should accidentally do the smallest first, just take the absolute value of it because you don't need to show any negative. And I find this value is 2.2. Now, is that a large number or a small number? I don't know. Well, my biggest electronegativity value is 4. And this is 2.2. And I have some that are decimal numbers, so I'm thinking this should be kind of big. Why? Because I know potassium as a metal and chlorine as a nonmetal will form potassium ions and chloride ions to make the salt potassium chloride. And we remember, if the difference is large, it's likely to be ionic. For that, we need to create a scale that will let us to determine the spectrum of bonding. Things aren't exactly ionic or covalent, black or white. There's all kinds of variations in between. And where a value of electronegativity difference falls on this scale or continuum gives us a lot of information. So we're going to set up our scale just like a number line, and we're going to start with the origin at 0, and we're going to put a number 1.8 about right here, and we'll just put a large number down there on the other end. When we talked about small differences in electronegativity, we talked about that being an indicator of being covalent bonding, where electrons are being shared equally. And we're going to have a cutoff around of electronegativity difference, and this is electronegativity difference of about 0.4, and this area would indicate the area where you have pure covalent bonding. We're going to have another cutoff. We're going to call this 2.0. And anything in this region, we're going to have completely ionic bonding. But what about everything in the middle? Well, like any artist knows, if you take blue and you mix it with yellow, it appears to be green. So what does green mean? This is a range that we know as polar covalent bonding. Polar covalent bonding simply implies an unequal sharing of electrons because one of the values for an atom or element is bigger than the other. It means that that element tends to pull harder on the shared pair and hold the pair closer to its nucleus than that of the other one. In ionic bonding, you remember there was no sharing at all. The electrons are completely lost by one atom, usually the metal, and completely gained by the non-metal to form positive and negative ions. And we learned about covalent bonding as the sharing of electrons to complete an octet. So covalent or non-polar covalent is an electron pair being equally shared between the two atoms that are forming the chemical bond. What is happening in this 1.8 to 2.0 region? Well, one thing I want to point out is that this also might be ionic as well. And this would be the case if a metal is present. If a metal is included, the likelihood of it being ionic is much greater. And if there are no metals involved, it is more likely to be polar covalent. You'll have to look at what's being given to you to find the electronegativity difference. If one of them is identified as a metal and the difference between the values is larger than 1.8, call it ionic. If the materials are two nonmetals or perhaps a semi-metal and a nonmetal, and the difference is between 1.8 and 2.0, you would label it polar covalent.